In computer science, a stack is a foundational data structure. It operates with rigid, predictable, and strictly sequential logic. But if you search through Python's standard library, you won't find a native stack primitive. Python does not provide a built-in stack data type the way lower-level languages like C or Java do. Even though the language omits this primitive out of the box, engineers still need a way to enforce last in, first out, or LIFO logic. The solution is not to build a stack from scratch. Instead, developers take a pre-existing dynamic structure and deliberately impose behavioral constraints over it. The underlying engine used to emulate this strict LIFO behavior is simply Python's standard list. This emulation works because of the specific physical memory properties of lists, specifically how they allocate and modify data in place. A Python stack is a standard list operating under strict self-imposed rules. This codebase provides a complete working Python stack implementation, achieving LIFO logic in just a few lines. We start with an object-oriented class definition to create an isolated environment for our data. This class wrapper acts as a protective shield. It hides the underlying list, preventing standard array operations from interfering with the stack logic. Inside this environment, the code defines 4 essential methods: push, pop, peek, and isEmpty. Notice that none of these methods require complex memory management or custom pointers to function. Every single one of these custom methods maps directly back to a native, built-in Python list operation. By deconstructing this class, we can see exactly how list mutability natively solves these theoretical problems. Before analyzing the operations, we have to establish why a list is uniquely qualified for this task over other sequences, like strings or tuples. Strings and tuples are immutable ordered sequences. Once they are created, their physical state in memory cannot be altered. Requiring a new memory allocation every time data is added makes immutable types inefficient for dynamic data structures. Lists, however, are mutable. They are capable of in-place modification, allowing them to expand or shrink without destroying the original memory block. Look at the initialization of our stack class here. By setting self.items to an empty list, we instantiate a blank mutable canvas that will absorb all future operations. Mutability is the foundational requirement. Without the ability to alter state in place, these algorithmic structures become far more complex and less efficient. Now we can look at the theoretical push operation, adding a new element strictly to the top of a stack. At the bottom of the script, the program executes this operation twice, pushing the values 10 and then 20. Tracing that execution up to the class definition, we find the push method. The critical execution line is self.items.append. Python's built-in append method handles the memory insertion logic automatically. Specifically, append targets the terminal end of the list. When the value 20 is added, it slots exactly into the newly created rightmost index. It does this without shifting any existing elements or requiring a manual index counter. This means the rightmost end of the list physically functions as the top of our stack. Because this is an O of 1 operation, it remains efficient regardless of how large the stack grows. The push method isn't inventing new logic. It simply applies append to satisfy formal terminology. The inverse is the pop operation, removing and returning the most recently added element. In the code, the pop method calls the built-in list method of the same name. Python lists natively possess this capability, which matches the LIFO requirement exactly. The key is the pop method's default behavior when we don't provide an index argument. By default, it targets the absolute end of the list, the last item added. The value is extracted, and the list boundary shrinks to close the gap in memory. This is the power of mutability. The list handles its own memory cleanup in place. To prevent errors, the code uses a conditional check, if not self.isEmpty. Attempting to pop from an empty list triggers an index error. This check prevents a crash, mirroring what theory calls a stack underflow. Python's native pop allows for LIFO retrieval without requiring us to manual pointers. Finally, the peek operation allows us to view the top item without removing it. Looking at the peek method, we see how this observation is handled. The method returns the item at index -1. In Python, -1 dynamically references the last item in a sequence, regardless of its length. Unlike the pop method, Bracket indexing reads the data without triggering a mutation. By leveraging negative indexing, we observe the current state of our data structure without altering it. Standard Python lists are highly flexible. They allow you to insert, delete, and sort data at any position. But for formal algorithms, this flexibility can be a liability. A stack requires strict terminal access to ensure data is handled predictably. The real purpose of the stack class is to deliberately constrain the list's inherent flexibility. By wrapping the list and only exposing specific methods, we force the program to adhere to LIFO rules. Designing data structures in Python is often about limiting access to a flexible type, rather than building complex logic from scratch. The technical mapping is direct. Lists provide the mutability, while append and pop provide the stack logic. This approach drastically reduces development overhead compared to lower-level memory management. Recognizing when to leverage a list's mutability and when to protect it within a class is a core part of designing efficient Python applications. Understanding how to wrap and restrict a list's native methods provides a reliable blueprint for building predictable, ordered data structures within Python's flexible environment.